and then generalize this to the discussion of the unoriented solution. So, if you remember, we looked at the last lecture. We looked at the three diagrams that gave rise to tag keys. We looked at the cylinder. We looked at the Klein bottle, and we looked at the Mobius. This is this diagram. This is this diagram. And this is this diagram. Okay. Open strings identified without any orientation reversal. Closed strings identified with an orientation reversal. Open strings are identified with an orientation reversal. Okay. And in the last lecture, we extensively worked out the modular transform of this guy and this guy. And we found that it could be represented as closed strings as propagation of closed strings. And the chief interest between sources, the chief interest there was the tag code for the passless closed strings. And we found the relative normalization between the tag code from this guy and this guy. We found that the relative normalization was a factor of n squared and plus 2 to the power 26, which came from here, times some more. Okay? Both these were positive. N was the rank of the was the number of grains at the max, number of endpoints for the open strings. Okay, and this n square is just the fact that the open string had the cylinder diagram sees n square different species of open strings. Okay, now what remained was to analyze this guy, the Mobius string. Okay, so we're going to follow our philosophy of trying to use theta functions as little as possible. So we're going to try to deduce the modular transformation properties we need, okay, from physics. Okay, so firstly, let's remind ourselves what this diagram was. This Mobius strip diagram. In the normalization that we were adopting, we had a 1 over square root of 2. That came from the that came from the zero mode. And in addition, then we had the contribution from 0 point energy, which was just q to the power minus 1 by 54. And then we had the contribution from all the oscillators. And remember that orientation changed the sign of all oscillators. Right? So we had product over n, 1 minus 1, sorry, 1 over 1 minus 1 to the power n, q to the power n. Okay? So this was the partition function of the Mobius. The nth guy being represented, being the contribution of the nth oscillator. Okay. Now, I want to rewrite this in terms of something familiar. Okay? So this is how I'm going to do it. You see, this quantity here is a product over two kinds of. Let's represent this as product over n, 1 over 1 minus q squared to the power n, and product over n, 1 over 1 minus q squared, product over, okay, all integers, n belongs to integers, and product over n belongs to integers plus half. Q squared to the power, that's called n. Okay? It's clear that this thing is the same as this. We still got this one with T. Now, this is familiar. This is the kind of thing that we get from free bosons. But this is also familiar. It is the kind of thing that we get from free fermions, but in the numerator. Okay? Let's remind ourselves. Suppose we had a fermion in the NS set, and we were computing its partition function. Then what we get is exactly this modulo of plus 0 by h. Is this clear? So this object, once we account for 0 point energy, is exactly the partition function of a free fermion in the NS set. Okay. Now, those objects we dealt with a lot about 4-5 lectures ago. Hello? Hello? Hi, Spencer. Yeah. Spencer, I'm giving a lecture now. Can I talk to you after? No? Yeah. Okay, great. So, putting these together, so it's easy to put these things together. So it's actually more useful to deal with the square of this object rather than this object itself. Basically, because if you remember when we dealt with fermions, we dealt with the complex fermions. We dealt with two fermions. Okay, so this thing was to be square root of 1. So this object squared turns out to be the same thing as 1 over eta of 2it times z00 of eta squared 2it times z00 of where z00 is, this is the notation we had when we were discussing these fermion partition functions. Okay? If you remember, the bottom 0 meant we were in the LS sector, the top 0 meant that we were not putting a minus 1 to the end, which is the only case. Okay? And eta, we very rarely use this notation, but it's just the thing that you get from the bosonic string. So eta of q is equal to 1. Q to the power minus 1 by 4 times n over 1. And set 0, 0. So this statement is obvious up to 0 point energies, which works out. Thank you. Thank you. Okay, so the only thing that, just by looking at the oscillator products, this is obvious, right? All that remains to be checked is the 0 point energies. It takes a little going back to your definitions and checking. So that makes sense. Okay? Good. Now, what was the point of doing what is the point of working around in this way? Okay? The point of working around this way is that we know what the transformation of both eta and z00 is under t goes to 1 over t. Okay? So, under the modular transformation, which we can basically rewrite in terms of an S, which is 1 over 2t. Okay? So, what we get is eta of I times s squared times 1 over times z00 of I times s, where s is 1 over 2t, plus whatever factors that you get from the square root 2 that t is this. Eta by itself is not 1 unit, right? It's t to the 1/4 times eta is 1 unit, right? Okay, so we have to replay the same games that we played last class on this object. Okay, so as we've seen, you remember how it worked last class, right? The square root t can be written as t to the 1/4 times t to the 1/4. Okay, so the t to the 1/4 times the eta will give you the modulo and everything, so it will be replaced by s to the 1/4 times the eta function of s. But that s to the 1/4 is 1 over 2t to the 1/4. So up to some factors of t, some factors of 2, it cancels. It cancels the t to the 1. Okay? So you play the same game on this guy. I'm not going to go over the factors of 2 as carefully as we did last class. It's just the same story. Okay, it's the same story that you have to replay again. And so this thing essentially turns it into this. Okay? Once again, then, up to some factors of 2 which you have to work out very carefully, this turns into ds itself times this eta of is times z00 of is with some number. This is squared and this power, but actually we had this whole thing to the power 24, right? So this is to the power 20. So this is to the power 24 and this is to the power 20. Okay, is this clear? Okay, there's one business about what the normalization of this s is that I'll tell you. Like the issue we dealt with last class. So with what s variable should you work? We have to determine that by physics. But otherwise the rest is algebra. Okay? Unless someone feels very uncomfortable, I'm not planning to work out the factors of 2 and tell you the answers. It's basically just exactly the same algebra. This last class. You get some factors of 2 from these square root 2s. And additional factors of 2 from keeping track carefully of how you do the modular transformation. Okay? Fine. Okay, so this is what we did. So now let's look at what the tadpole for this diagram looks like. Schematically. You see, there's one very important point that I want to highlight. And that is this. This z00 to the power of is to the power blah 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 is what? So as always, what we get is there's ds, then there is e to the power s times t. This comes from the tachyon mass. The 0 point energy is negative. And then there is a power series in e to the power minus s. The closed string tadpole comes from the term that is in which this e to the power st is cancelled against the e to the power minus s. Okay? But what's very important is that you see, in this object here, let's look at it in the original diagram. In this object here, what we would have is a q out here, a q to the power minus 1 out here, from the 0 point energies, once you raise it to the power 12. Okay? times an expansion from here in q squared. Sorry, e to the power st is the q variable, 2 pi st. So q here is e to the power minus 2 pi s. There's no t. So q here is e to the power minus 2 pi s, but there's a q inverse. Let's look at the original variable. It's the same function in this variable and that. So let's look at the original variable. In the original variable, we had a q inverse to start with. That came from 0 identity. As always, all the diagrams. And then this is a power series expansion in q squared. Whereas this here is a power series expansion in q cube, and so on. Right? Because this object is the partition function of a fermion in the ns sector. And so the oscillator energies are half, 3 halves, and so on. The argument of this is q squared. So half into q squared is 1. 3 halves into q squared is 3. I mean, it's even more balanced from here. Yeah. Right. Okay? Yeah. And the key point is, and the key point is that the only way you get the master's tadpole is by cancelling the term that's order q, which comes only from here and out. And the term that is q is 1 over 1 plus q. So when power series expanded, it gives you a minus sign. Okay? Gives you a q with a minus sign and then a 20. Sequence.
We don't care about the 1 because that's the
1 is the
taxon.
And it will not be there in the superstring. And all of last year I kept saying when we get to the superstring we'll see that. This time it's better. In this lecture we will see that it's not there in the superstring. Okay. The master's tadpoles are series. That's what we're working on. Is this minus sign thing? Okay, let me just say that in an equation. We had 1 over 1 plus q. This term also has 1 plus q cube and 1 plus q to 5, let's see that. To the power 12. And then we had a q inverse, yeah? We power series expand this to get the term that's independent of q and we get minus. Okay? So this is the first realization that the tadpole from this diagram is negative as compared to the tadpole, or in the convention in which the tadpole to the other two diagrams are positive. Okay? Now the next thing to do is to carefully run out the factors of 2, the relative factors of 2 between all these things. Okay? I'm just going to quote it for you. Yeah? So in the conventions in which we worked, in which there was an overall factor of 2 outside, then there was a ds divided by s. The positive terms, the tadpoles from the positive terms, which were n squared, and 2 to the power 26. Here, we've got some independence that we still have to determine. Okay? But apart from that is 2 into 2 to the power 12. To the minus. The dipole term. It's 2 into 2 to the power 13. Apart from the n dependence that I'm going to tell you about now. This would be 2 n. Well, it's 2 to the power 14, but I'm writing it as 2 to the power 14 for a reason. Thank you. 2 to 2. Okay, now what about the n dimensions? You remember last time we talked about Chan pattern factors on the unoriented bosonic string. And we talked about the two possibilities. The possibilities were that either we had orientation reversal acting on the Chan pattern factors simply as transposition, or transposition by conjugation with the symplectic matrix. Okay, so let's look at the case where it acts just by transposition. Okay, in the case where it acts just by transposition, then we get an additional factor here from the trace just over the Chan pattern. What we have to compute is trace of omega on the n cross n on the n squared dimensional vector space of Chan pattern factors. But this n squared dimensional vector space splits up into two spaces. The space of symmetric matrices, which is n into n plus 1 by 2 dimension, and the space of antisymmetric matrices, which is n to n minus 1 by 2 dimension. On the first subspace, omega acts as 1. It just transposes. On the second subspace, it acts as minus 1, because it anti-transposes. Okay? So the trace of omega is the dimensionality of the first subspace minus the dimensionality of the second subspace. Number of symmetric matrices minus the number of antisymmetric matrices, and that number is n. There are the diagonal elements that can be only symmetric. Off diagonal elements, you can be either symmetric or antisymmetric, as many of those. The diagonal elements can only be symmetric, so there are even more symmetric matrices than antisymmetric matrices. Okay? So if you work it out for this case, where omega acts with the transposition, just as transposition without conjugation by the symplectic matrix, this factor is simply. Again, I'll leave it as an exercise to work out what trace of omega is in the case where you conjugate by transposition with similarity transformation with the symplectic matrix. All it does is flip the sign. Turns out that since this is the SO case, it would be plus for the SP case. Okay, so this tachyon here, this tadpole here, now has a very simple form. It takes the form n minus 2 to the power 13, the whole thing squared, n minus plus 2 to the power 13, the whole thing squared, times 4. Okay? And this minus plus, it refers to SON and SP. So what do you conclude? We conclude that the SPL theory always has tachyons. However, the SON theory does not have tachyons if n is chosen to be a very particular value. That is 2 to the power 13. Okay? So through this exercise, we've discovered another potentially consistent bosonic string theory. This potentially consistent bosonic string theory is the bosonic string with 13 D25 branes in the background. That is, open strings allowed that can move around all of space-time, but 13 different possible chanting patterns. Okay? With orientation reversal acting on both the open string and the closed string sectors. This theory does not have any, it has modular invariance as it should be, because modular invariance is a concept that applies only to the cylinder, only to the torus diagram, and that's the same as for the ordinary bosonic string. And it's as tadpole free as it should be. Meaning it has no tadpoles for massless fields. Okay? Now for the bosonic string, there's no more one can say. theory is not consistent. Excellent. There's a corresponding theory in the superstring. It's going to turn out to be one of the consistent string theories.
So the Bonai string theory, of course, closed strings will also be there.
Of course. Closed strings are orientation projected.
No, I think that, of course, you consider the cylinder, the triangle, and the movie string. And along with this, the sphere will also be there.
No, the torus. We didn't want to diagram. The torus will also be present. Yes, it's present, and we didn't look at it in this context because it's
It doesn't contribute to the diagram.
Exactly. Yes. Excellent. Okay. Now there's just one little thing. I really want to complete our discussion of open strings today. Anyway, so there's one little thing that I want to tell you about. Before we, okay, but there are two physics things. The first one is the following question that you might have had. You might have had the question, look, could I have had a theory in which the closed strings for orientation projected, but the open strings were oriented? Okay? You might have wondered, is that, could that have been possible? Okay? And the answer is no. The intuition behind it is that, look, if you've got an oriented open string and another oriented open string, if you combine together to give you an oriented closed string, which would then be a contradiction if oriented closed strings weren't part of the spectrum. Okay? But there is a more sort of straightforward way of saying it. I'm just saying the same thing but in different language. See, suppose that you didn't have the orientation projection. So that in the open string sector there was only the cylinder diagram. Then if I take the cylinder diagram and I do the modular transformation of it, I get what I got for closed string exchange, just in the ordinary closed string, in the ordinary Laurent string. And that involves the exchange of all closed strings, and not just oriented closed strings. So the open string one loop diagram, when reinterpreted in the closed string channel, would be inconsistent if your closed strings had only oriented closed strings, but you had unoriented open strings. Okay, it's something that one can check, though I won't try to do it. It's a nice, not difficult exercise given the formula we have here. That if you take the unoriented open string, you look at the sum of the Klein bottle, the cylinder, and the Mobius strip, and then you look at the exchange between the effective sources between these things. The only things that run across channels are unoriented closed strings. So this is a consistency check. Okay, we've not done the action check. It's a nice exercise. However, this part, that it's impossible for the open strings to be just what they were. So, okay. The last thing, I can't remember, we did this. Did I draw this diagram that reinterpreted the Mobius strip as an exchange between closed strings? So let's do that. So we have this open string which has pi and 2 pi times lengths 2 pi times t, and we have this. Now, like for the Klein bottle, let me take the subject cut it to the middle. Okay, so I'll write this as this, and this is this. Now, like for the Klein bottle, I'll take this object here. Oops, I'm not sure about orientation. So this is this way, and this is this way. Sorry. This is this and this. Sorry. Okay? Now, I'll take this object, turn it around, stick it to the bottom here. Okay, so what do I get? I get this. And I get this. I turned it around, stuck it to the bottom. Like this, such as that. And this object here is this. Is this clear? So now, firstly, what are our lengths? Our lengths are pi by 2 and 2 pi into 2t. Okay? So the lengths are pi by 2 into 2 pi into 2t. And what is this diagram? You see, this end is identified with this image. We've got some sort of cylinder. At this end, we just have a straight line, which is just saying ordinary open string boundary conditions. At this end, however, we have the cross cut. Okay? We have the cylinder with the instructions that we identified diametrically on the sides. So this object now is a cylinder, at one end of which we have ordinary open string boundary conditions, and the other end of which we have the cross cut. Okay? And what is this modular parameter? Now, in looking at it as close to thing, we always normalize this length so that's 2 pi. Okay? So normalizing it this way, we get a cylinder with a ordinary finger across here, and the length to which over which it travels is 2 pi over 8. So we divide by 1 which is p. So S, depending on your dimensions, is either 2 pi over 8t or 1 over 8t. For this guy. How do I get the first step? Let's look at this diagram in a few steps. Let me draw it in different colors. So I have this and this. Now, what I'm doing is taking this thing, which is unchanged, and let me take this object and flip it around. At the moment, I'm just flipping it around and drawing it. So if I flip it around, these arrows are assigned. So this goes, oops, should be consistent about this. These arrows are assigned. This quantity continues to pop up on that side. This quantity is straight, and this quantity is straight. Sorry, this quantity is, this was this single. Now this, the fact that both these have double arrows are the instruction that we're supposed to identify these two edges. So I just draw it together. Okay, so now what do I have? I have this. This is the statement that this length here has to be identified with this length. Now, had this been done all through, this would simply have been a cylinder of half the length. But the identification is only at the edge. So the cylinder length keeps its length. It's just the edge is funny. The end is ordinary open, the edge has boundary conditions that whatever you have one part of the circle is the same thing diametrically opposite. And that's what that cross cat means. That this point is identified. Okay? So, you see roughly why what we saw working could work. What was the exchange? The exchange between, for the client bottle was the exchange between two cross caps. The exchange for the cylinder was the exchange between two open string combinations. Here what you have is the exchange between one cross cap and one open string. Okay? So, it seems reasonable that client bottle plus this plus cylinder could be a perfect square. If you think of the contribution from cross caps as A square, contribution from this open string combination is B square, this is like an AB. Okay? And, just as we tend to separate out the contribution from different agitating factors and say this comes from a different brain, one might be tempted to separate out this 2 to the 13 as a contribution from 2 to the power 13 different orientifold planes or something like that. Okay? We'll discuss in what sense something like this can be done as we go. Okay, we'll try to give a sort of more physical understanding of the 2 to the power 13. Okay. But I hope to have made it reasonable that these things can cancel each other, roughly because the structure is tightly connected. Okay? And we've gone through the details. Okay, any questions or comments before we turn to discussion?
Going back a little bit further. So, in any physical theory where you don't have the dipole, the other kind of condition where you have this simplistic matrix that is just
well, as long as this brains are space. You see, okay, it's a good question, and we dealt with it last year, actually even in your exam, if you remember. But you see, the condition for having a dipole is very serious if this dipole fills all of space. But it's not serious if it's a small codimension defect in space. Suppose you have a dipole for the graviton localized at a point. What does that mean? It just means you have a point mass. Any massive object is a dipole for the graviton. Gives you 1 point. And certainly, I mean, it's not an inconsistency to have a massive object in the thing. Why is it not an inconsistency? It's not an inconsistency because this object sources the graviton, but that graviton dies off as you go around. It's a localized source of graviton. Is that clear? Actually, so if you think about it, the object that sources the graviton should be codimension 3 at least. See, suppose it was filling all of space, that's a problem. See? Suppose it was localized in 1 dimension in space, that would, roughly speaking, you have to solve the equation del squared phi equals 0 to get a gravitational potential. And in 1 dimension, the del squared phi equals 0 has a potential that goes linear. In 2 dimensions, it's a log space, it's a log. That's not good. But in 3 dimensions, it goes like 1 over r, and then by 1. So, you can have objects that have dipoles as long as they codimension 3. Effectively. Okay? And then those objects can, and in general, in some situations, will have the SP. Okay? It's just that for the space filling guy, where we needed to cancel the dipole, that was not. It's not true that the SPs will play in the role instrument. Okay? You remember, in fact, it was the dipole calculation that allowed you to compute the tension of the units. Because dipole was the source of the graviton, you computed that. Found. So, right. Okay, good question. Other questions, boss? We're going to let's postpone that. It'll be lightly rate. You'll have localization in some dimensions. But let's see. Okay. Fine. So now we want to continue with our discussion of the superstring. This was all an aside to fill up a gap in our something we hadn't talked about right away. Now we want to return to the superstring. So, if you remember a few lectures ago, we classified, roughly speaking, with the various assumptions, we classified all consistent superstring theories, which had only flow strings. Now the question we're going to ask is, can we make a superstring theory which has open strings and is consistent? And we're going to follow our discussion of the Bosonic string. But before that, we should talk a little bit about fermions with boundaries. Okay. So consider this. Consider, just in Hilbert's-based language, we've got a string which is a strip, goes from 0 to pi, and there's the sigma. The first question I'm going to ask is, what boundary condition should I impose at fermions when my worksheet is boundaries? Now let's remember what our action is. So our action was 1 over 2 pi psi del bar psi plus psi bar del psi. In Euclidean space, in Lorentzian space, which is probably more appropriate for this, this is del 0, let's say, plus del 1, or that's minus del 1, and this is del 0 plus 1. Okay, now what was the principle that allowed us to compute allowed boundary conditions for the free boson? The principle was that we wanted this action to give us the correct equations of motion. To give us. Okay. So for that, we wanted to be able to vary the action and have surface terms vanish in that direction. So when we vary this action, there are two places of variation can do. Well, four places. Here, could hit here, could hit here. If variation hits here or here, it just gives us copies of the equations. That's not. Variation hitting here and here is not. Okay? Now let's see. So we're interested in the contributions from some boundary. So let's say the boundary is 0. When we have this variation here, what we normally do is take this derivative, transfer it here by integrating by parts. But that thing has a boundary term. So let's write down the boundary term. In this case, the boundary term is minus psi delta psi times this overall constant it is. In this case, it's plus psi bar delta. This is very analogous to what we saw with the boson. Where the place of psi and delta was played by del x. Right? And for the boson, we said, well, there are two things we can do. We can either make sure that delta psi, delta x is 0 at the boundary, or we ask for the normal derivative of x at the boundary to be 0. Now, neither of these conditions make any sense here. Because the equation psi equals 0 is not a very well defined thing. Because basically, psi does not take its values in numbers. Psi is a class-mark variable. Okay? It's questionably meaningful and certainly very unnatural to set it to 0. However, there's something else we can do here that is very natural. And that is to say, psi is equal to plus minus psi. Psi and psi bar both are anti-causative numbers, so they can be set equal to each other. Because everything here appears as a square, the plus minus doesn't matter. Okay? There's a relative minus sign between these two. So if we take psi, if we set psi equals plus minus psi bar, that really works, right? That cancels these boundary terms. So now there's the question of whether we should set psi equals psi equals psi bar, psi equals minus psi. We also have two choices. We have a choice here, this boundary, and a choice in this boundary. Now, suppose we did the following. Suppose we said psi equals minus psi bar at this boundary and psi equals minus psi bar at that boundary. Then we could make a variable change. Psi bar is equal to minus psi bar here. The action is quadratic psi bar. So we'll change the action. And that will change our boundary conditions to psi equals psi bar. So what we're seeing is that the absolute boundary conditions of these two boundaries is not important. What's important is the relative boundary condition. If we set psi equals psi bar here and psi equals minus psi bar, then no variable change to get rid of that. Okay? So physically there are two distinct variable boundary conditions we could impose. And the physically distinct boundary conditions are, let's say they're always at 0. We set psi equals to psi bar at sigma equals 0. But at pi, we could set psi equals plus minus psi bar.
Let's say that we can't say this delta psi equal to 0 on this boundary, right? So what happens to the picture in which, so when we actually set Dirichlet boundary conditions and the generalization of that in this question, so you're saying that that's not possible somehow here, or?
Yeah, I mean, right. The Dirichlet boundary conditions apply only to those bosonic systems.
If we, now, so, because those are the coordinates and
right. You're localizing something in space. Start. There's no equivalent statement for psi. See, these are the possible consistent boundary conditions.
Okay, the 0 then, okay, so I didn't understand quite the logic that since it is Grassmannian, it can't be 0. I mean, in Grassmannian variables, you have 0, right?
Yeah, okay. Why can't you say it?
If you take a superspace kind of a picture and think of this B-brains as some kind of localized object in the superspace, then the fermionic coordinates in that superspace will be related to this psi by some kind of bosonization. Isn't that true?
There's a very complicated relationship between the fermionic coordinate. This is not a fermionic space.
I understand. Yeah, I understand. But this would be somehow really. I mean, there should be an analogous statement of B-brains in superspace.
Even in superspace, you don't localize in fermionic coordinates. So only localize in bosonic coordinates. The only sense in which you localize in fermionic coordinates is that some supersymmetry is annihilated. That's the analogous statement to some translation operators annihilated, right? Some supersymmetries don't annihilate it, like that's the analogous statement to some translations not annihilated. But I should answer your question about just technical thing. about setting, just at a technical level, why couldn't you just set psi equals 0? The question will be, what reverse space interpretation that thing has? Suppose you have a formula with a path integral, where in the path integral you set zeros at some ends. The issue would be, whether you can give this a reverse space interpretation. A good way to answer that question. It's such an unnatural thing to do. It's certainly considered to any other value. In a sense, psi to 1 makes no sense. It's true 0 is special. Because in the end, psi is some number in it's a vector space, you can multiply the zeros. It's true it's special. But it's very unnatural. And I think that unnaturalness will turn into the statement that if you take a path integral here with this enforcement and try to cut it and give a reverse space interpretation, it would exist or will have some trouble. Okay, but it's a good. I should think that through. Let me try to give you a better answer. That's a good question. Let me try to give you a better answer. I realized actually as I was saying it that 0 was a special. Okay. Yeah, there. The way I would try to address this question. Let me just do it. Let me give you a better answer.
It would mean some kind of a localization again, right? So because if you think of a space which is like formed of the x's and the signs, the theory space that we think about, just from if we are not motivated by these things. So
they are not motivated by what?
This kind of string theory picture where we have our space.
Right.
We can think of it in that sense that we have a theory space where we are dealing with all the fields.
Right.
So in that space, it will mean some kind of a localization, and I don't see why that can't be. Given there can be localizations in XU spaces. Because as you say, from the space-time point of view, these are just some.
Maybe it should be true. Okay, let me think about it. I'm not even 100% sure of the statement. Maybe, actually, if you just think of it in terms of a mode expansion, it seems perfectly legitimate. And now Jyotirmoy's point is that when you have Dirichlet boundary conditions for X, how can you not have this psi? If you want to maintain supersymmetry, maybe that's right. Maybe that actually is what happens. Okay. Let me think about it. I probably made the wrong statement. And in fact, thinking about it is probably wrong. I think psi equals 0 may well be a legitimate thing to do. However, okay, let me look at it. I think Jyotirmoy may well be right. Psi set equals 0 may well be a legitimate thing to do. However, that's not what we want to do here. Okay? At least it's not what we want to do if we're looking at the supersymmetric completion of the open superstring. Okay? Why not? Okay? Why not? Well, let's retreat one step and ask him for us our theory to maintain worldsheet supersymmetry. Okay? At least from that point of view, it's going to be totally clear. Let's see why. Okay. You see, let's try to now look at this theory from the point of view of the doubling trick. Suppose I impose the boundary conditions I had here. Suppose I impose boundary conditions that Jyotirmoy wanted. Let's say psi was equal to 0, psi bar was equal to 0, something like that. Then what we could have is some modes living in the open field sector between 0 and pi. And the boundary conditions were in psi and psi bar. Okay? With some particular boundary conditions. Okay. On the other hand, what are we going to get here? You see, what we see here is that what we said is that psi is equal to psi bar. So now let's define this bigger field. Psi is, let's call it big psi, is equal to psi from 0 to pi. And is equal to psi of sigma is equal to psi of sigma from 0 to pi. And is equal to psi of 2 pi minus sigma. Psi bar of 2 pi minus sigma from pi to 2 pi.
The radiation of that will have psi bar second.
Psi bar del second.
Yeah, not del psi bar.
Right. Okay, so I define this double field that looks like this. Then what are the boundary conditions of the double field? Firstly, it's a sensible thing to define this double field like this, because at pi, it's continuous. Okay, let's say that my convention was that at pi analysis and here it was supposed to be this. Okay, so at pi it's continuous, and then when I come back to 0, what boundary conditions do I get? When I come back to 0, what boundary conditions I get are big psi at 2 pi is equal to plus minus big psi at 0. Is this clear? This is big psi, it's not second. The plus minus means the same as this distance. Okay, so what are we seeing? What we're saying is that the doubling trick works for fermions as well with these boundary conditions. Okay? You think of it as a single fermion living from 0 to pi, up to 2 pi, but that single double fermion has either the Raman projection or the NS projection, depending on whether this is plus or minus. So the effective boundary conditions of that doubled fermion are either Raman or NS, depending on whether you have both plus or both minus will give you Raman, 1 plus 1 minus will give you NS. Okay? Now the Raman sector is the supersymmetric partner of the open string, of the bosonic field of the open string. Because that was just a single boson from 0 to 2 pi. Yes. So if you wanted the super partner of that would be a single fermion from 0 to 2 pi, periodic boundary conditions. So clearly this is the thing that we want to do if we want supersymmetry. Of course, this argument, as Jyotirmoy pointed out, does not work when we have deletion boundary conditions for the bosons. So I would have to rethink it. It could be the okay. I'll get that. But anyway, in the context that we're working in now, this is true. Okay, great. Now, so now we understand our open string fermions well. Either you have psi is equal to psi bar at both ends, in which case you've got effectively a single Raman field, or you could psi equals psi bar 1 and then psi equals minus psi bar the other, in which case you've got a single NS. Now, the next question one could ask, okay, the next question one could ask is, okay, so we've got this open string. We'll understand how to find the fermions of the open string. Now, when I try to do calculations with this open string, should I be imposing some sort of GSO projection of the open string? Okay, and the answer is yes. And the answer is yes, for a very very obvious reason. So let's look at the cylinder thing. Okay, suppose I didn't impose a GSO. So then, the only boundary conditions I would allow my fermions are antiperiodic as we go around this cylinder. Fine. So it would be antiperiodic as I go around here. But reinterpreting that as a closed string channel, that will tell me that the only closed strings that propagate will be NS-sector closed strings. So we already know that our closed string theory has both NS and Ramon sector closed strings. Okay? So, in order to be consistent with that, this one loop diagram should have both NS and Ramon sector closed strings probably. Okay? How do I get the Ramon sector? First, simply by including in the diagram with -1 to the F, the -1 to projection, F projection, yeah? That will make a fermions periodic around this cylinder side. And therefore will give us the Ramon sector. This is the case. You see, suppose we do trace of 1 plus -1 to the power.
So you take the whole spectrum and you so as to get the NS and the
Yeah, the GSO projection on the open strings is the thing that will allow both NS and Ramon sectors to propagate in the closed string. If you didn't have a GSO projected, you only have NS sector closed strings running in the closed string. Is this clear? Now, of course, that might not be very serious purely for the vacuum diagram. But it will get very serious when you put arbitrary operator insertion. Because it will mean there's nothing you can do to produce a Ramon sector closed string, which we must. Okay. Well, why should you be able to produce the Ramon sector closed string? Well, you could check that explicitly by scattering amplitude calculations. You know, if anything is sourced under, so there's an amplitude that produces a Ramon sector state. Okay, that produces a Ramon sector state. I mean, it's not true that you can't produce strings. For instance, these brains, as we'll see as we go along, are charged under form fields. The ripples of these brains source these form fields. These ripples are open string vertex operators at the ends of these brains. No, but we just do by scattering amplitude. Oh, so you're saying that what if there was a theory in which all no, yeah, you see, suppose we didn't impose the projection.
Open string should definitely source or else not
definitely source gravitons, and
why should they necessarily source other?
But let's say this. Yeah. The projection from the open string point of view just reduces the number of open strings. Okay? So, if you have a diagram in the projected theory, which has open strings producing a Ramon set, just take the closed string, that diagram would exist in the unprojected. Just a three-level scattering amplitude. I'm not doing any modular transform. Yeah, see, first came, there exist processes in which open strings, in the usual case, in the usual projected theory, in which open strings scatter to give you Ramon set closed strings. Second claim, you see, suppose we didn't project. Then what would we have? We have more open string vertex operations than we had if we didn't project. So, one could continue to consider the amplitude.
Because you have more states. Now it might happen that to make consistent theory,
You're saying, why don't we do something else? Some other. I'm just saying that we could not. Okay, it's not inconceivable from my argument that some other process would do it. I'm saying that if you modify the theory in some other way by introducing some other projection.
let's say we don't care about the GSO projection.
Yeah, so let's look at that. Suppose we say that we've got a theory where we've got the open strings which are not GSO projected and the closed strings which are GSO projected and nothing else. Okay. Then every scattering amplitude that exists in the projected theory also exists in the unprojected theory. Okay, and it's the same fact. It's this inheritance. Okay? So in particular, you can show just by explicit calculation that you can produce Ramon sector closed strings by scattering open strings.
What is the calculation which
Just a disk diagram.
Oh, without the modular.
There's no modular transformation variable. It's tree level. It's just this. So such a thing does happen. So this would be totally inconsistent. Okay.
This diagram
We'll show that we produce these things, so then how do we solve that? Is this clear? Okay. Now, there is also the other question of there's also the other question of do you want to impose? So we talked about how you need to have you need to GSO project. You need to GSO project this guy, and we also let's see. See? Okay. I suppose what I want to argue is that we should have both the NS and the Ramon sectors in the universe. And the Ramon sectors in the open string. We know that that's true of the closed string. We've done a systematic classification. And now, why is that? Let's see if we can do this. Let's see if we can do this from this one. What would go wrong if we, in the open string vector, something would certainly go wrong by trying to use this. I should just take that from offline. Let me make the assumption here that we're going to look at open string theory by looking at something with both sectors. Okay. I suppose as we proceed with our calculations, we sort of see why it couldn't have been otherwise. That would cancel. Let me proceed with this. There's probably some strict things to say that would immediately convince you. It should morally be related to. Okay, I'll tell you what my suspicion is. I haven't checked it, but my suspicion is that if you didn't have both the NS and the Ramon sector in the open string channel, when you did the cross diagram, you would find that the states that propagate are not GSO protected in the first channel. Right. Because this boundary condition turns into that boundary condition. So I'm almost sure that's true. But I need to check that. But I think that's what would go wrong. I think that's what would go wrong. That suppose you have only the NS or the Ramon sector in the open string channel, then you do this cross diagram and you see all the poles that you get, you find that you won't get the JSO protection. Okay, so this will force you to sum over both sectors in the open string channel. Okay, good. I think that's right. Okay, good. Fine. So now we have our theory well understood. We have our boundary conditions under control, and we understand that we have to both JSO project and use all sectors. Okay. So now that we've got all of this under control, what we're going to do is to try to produce a consistent open superstring. In order to produce this consistent open superstring, we're going to mimic what we did with the bosonic string. So what we're going to try to do is to do an once again, if we just introduce open strings without any orientation and reversal, we get close to entangles. Okay? The calculation will be very simple and bosonic string, and won't make sense. So you need some mechanism to get to these entangles. And what we're going to do is to imitate our discussion of the bosonic string. Okay? So in the bosonic string, what do we do? We orientation reverse projected and then inclusive open strings. Okay? As we argued, the open strings have to be orientation reverse projected as well. So let's try to do the same thing. Okay? So what we want to do now is to study now the closed string theory we have type 2, in superstring we have type 2A and type 2B theory. Type 2A theory with different JSO projections of two different sides. Type 2B theory with the same JSO projection of two different chiralities. We're going to orientation reverse That's exchanging left with right movers. So we need to be dealing with type 2B theory. Because you can't orientate, you can't exchange left with right movers if you're doing different projections. Okay, you need to be dealing with something that is left and right symmetric if you want to endorse this flip. So, what we're trying to do is to gauge the theory by a symmetry of the theory. So that would not be a symmetry of the theory. That would say then that you do some orientation reversal, and it takes a type 2, it takes one kind of type 2B theory to another kind of type 2B theory, a type 2A theory to another kind of type 2B theory. What we want is to take some object that is a symmetry of the Hilbert space and gauge out of it. That's not true of the type 2A theory.
If I change the left to right,
But that's your changing. But the reversing the JSO projection is changing the theory. I want a given theory, a symmetry of that, which I gauge. The GSO projection is part of my definition of the theory. With the theory, with this GSO projection, if I try to do this omega flip, it doesn't take me to state in the same theory. It takes me to state in another theory. The theory would have done this reversal. You see, what are we going to do? We're going to identify left movers with right movers. That's what this projection onto omega is. This 1 plus omega by 2. It identifies left moving oscillators with right movers. If the set of left moving oscillators and the set of right moving oscillators are different, how can you do that?
yeah, they are definitely different after the GSO.
That's true. The JSO projection is part of the definition.
What I'm asking is, why can't we do simultaneously? Why should we first do the GSO projection and then do an implementation? Why can't we just take the unprojected theory?
Take the unprojected theory, and then do an orientation flip. That's certainly allowed.
Then do a projection. Okay, using both the orientation, using the combined orientation flip that is used.
Using the combined orientation flip plus the JSO. So try something more general than this. Let's say.
I don't understand this because the JSO projection is different from the two sectors, and even if we specify a format in which the JSO projection transforms under this, if it is different from the two sectors, then there is no way in which we can identify it.
Yeah. The Logan is now suggesting something different. He's not saying do the JSO projection on type 2A. He's saying invent a completely new kind of superstring theory. One in which was not obtained by orientation projecting consistent theory. Okay. Let's start. Okay. But instead one which is obtained by some other procedure. So like the discussion that we had right at the beginning, include omega in that discussion. That's a more difficult question. Okay, let's continue next class.